Hi everybody, welcome to another video in Discrete Math, section 1.6, Rules of Inference. So let's look at this example. We talked about this earlier. We say, all men are mortal. Socrates is a man. Is the conclusion that Socrates is mortal? Of course it is, but I will focus more on how we prove something like this. Right. Of course, if we can write this in terms of the premises, like each one of these, and then the conclusion and the last one in the predicate logic. So we say for every people, whatever we substitute in, if this is true, and imply that every man is moral. So that's pretty much what he said. And then Socrates is a man. So this is true when we substitute Socrates in it, and it turned out to be true. And when both of them are true, then Socrates is moral. Right. Now, of course, we focus on that a little bit later, more specific. But now, let's go over some terminology. We have an argument. It's a propositional logic, which is a sequence of proposition. The last one is called the conclusion. Everything before that is called the premises. And the argument is valid if the true of all of this implies the true of the last one. And an argument form is an argument that is valid no matter what proposition I substitute into its proportional variable. If we have P1, P2 on to Pn and lead to the conclusion of Q, then this is a tautology. Right. Even though the definition it says every one of them true implies the last one true, but of course we can use this as a tautology, so we can substitute anything into it. It's still a tautology. So they kind of like two type of definition. One is the true imply the true, and then one of them is by the tautology. Of course, if it is a tautology, if we want to prove it, we can always use the truth table, but sometimes that takes too much time. So that is the purpose of this section. We go over some of the rules that will help us reach the conclusion, reach a valid argument without going through the truth table. Right. This section we learn a way to validate argument. Right. So we can use propositional logic. That's what we study here, or we use the predicate logic. That's what we used earlier. Right. Now back to the first example. I will write this again. For every x, if it's a man, then it's mortal. And it's a man. We draw a line, and then after that the three dot meaning therefore. Now just look at some values here. For every x, this is true. So if we put Socrates in here, and that of course implies that. So if we put Socrates here, and we have the man. So this pretty much, if we ignore all of the variable x here, and we just say if we have Socrates here and here, so we just have P imply Q, and then we have P already. Of course that will imply Q. Now if we write like this, it's easier to understand, right? So if we substitute Socrates in for x, of course if it is true for every x, it's true for when we substitute a person name into it, right? So we just reduce into that, and of course if P implies Q already, we already have P, therefore we will have Q. Right, so this is true, the valid argument. Of course now we talk more about the rules of inference. So Don't get too hung up on the name. Right. So look at the first one. Of course, when I typed the note, I didn't have the line. It's more difficult to draw a line, so I'm just going to draw that manually. Right. So the way we write that as a logic statement, when we see this, we write all the premises with the conjunction. And that implies the conclusion, right? Now, for this, of course, we just write all the premises. In conjunction implies the conclusion. Right, so we talk about this. If P implies Q, we already have P. Of course, we have Q. So that first part is easy. Now, this, if we have P to Q, and then we have not Q, then not P. So remember, contrapositive is not Q implies not P, right? So this is the contrapositive. P implies Q. So just like that, if we have not Q, then we have not P. So this is derived from the contrapositive. The next one, again, I will write all the premises. And that implies P implies R. So when we look at this, P to Q, Q to R, therefore from P to R. So like if we go from A to B and then from B to C, so that means we go from A to C totally. So that makes sense. More like the transitive properties. Right. Next, we have P or Q. Conjunction with not P. Right. So in this case, like I said, I want to write some note here. This is all. So remember the problem when we the example that I said about if you want to get on the cruise, either you have to get the vaccine or you have to have the proof that you have COVID more than 15 days, something like that, right? So if you want to get on the cruise, you have one of those two. If you're not having the first one, then it have to be the second one if you want to get on the cruise. Likewise, if you want this to be true, one of them have to be true. If it's not one, it has to be the other, right? So I said, so that's why it comes from disjunctive or disjunction, right? The note I want to write here is P or Q is true. One of them must be true. If it's not this, it have to be the other. I mean, if it's not P, it has to be the other. If it's not this, then it have to be the other. Sorry. Yeah. So that makes sense, right? Next, we have P imply P or Q. Now, the name of this is called the addition. So what do we add into it? So for example, I could say something like 1 plus 1 is 2 is true, and then I can just add any statement to it. The whole thing together is going to be true, because P or Q, if P is true, you can add anything to that, because you only need one of them to be true, right? So if P is true, you can add a bunch of things. So we say 1 plus 1 is 2, and that cannot use that. 1 plus 1 is 2, or I am a Superman. That one is true, because 1 plus 1 is true. It's good enough already. The whole thing, everything after the or could be anything. The whole compound statement together is going to be true if you have one of them is true. So that's why we call it addition. You can add whatever to it, it's still true. Right, so this, if that was addition, now this is like the simplification or the subtraction, if you will. If you have and this one is true, everyone have to be true. So say conjunction is true if every statement is true. Right? So if you have the whole connect with and is true, then one of them has to be, each and every one of them has to be true. So we only need one of them. Right. Likewise, the conjunction, just by the name, P is true, Q is true, then P and Q is true. Of course, that we only talk about the calculation, the N. This is just like I said. Oh, by the way, I have to write in terms of the compound statement. Now this one is obvious. Now P or Q and not P or implies Q and R, Q or R. Now this is a little more difficult. P, not P, one of them is true, the other one is false, right? So if P is true, then doesn't matter what Q is, that's one true. But not P is going to be true. So P is true, not P is false, then R have to be true. Bottom line is, because P or not P, one of them is true, one of them is not true. Forcing Q and R, one of them has to be true. Of course, both of them can still be true, but because one is true, one is false, one of them, at least one of the Q or R has to be true, and that's enough to say that Q or R is true. Right. So I'll just write a note here. P and not P, one of them is true. If one of them is true, forcing Q and R, at least one of the Q or R has to be true. Right. Now let's look at some example here and determine what is the rule that we use there. So it is below freezing and raining now. So we just say below freezing and raining now. Therefore, it is below freezing. Right, as you see, that is this one. It's called the simplification. Next, I'll either take physics or math. So physics or math. I did not take math. So therefore I must take physics. Of course you can write like that, or you can write P or Q, not Q, imply P. Yeah, you can write like that. And of course when we write like that, we know it is disjunctive, this one. I said it could be not P then Q, or not Q then P. Of course, if it's not one, it has to be the other. Right. Next, the team is good. So if it's good, it's P. Therefore, the team is good or lucky. But this is just an addition, right? So if P is true, we can add a bunch of statement to it in the junction. It's still true. I'll just write the name for it. So what's this name? Okay, disjunctive. And this one is addition. Next, live in Dallas, P, and Dallas in Texas, Q. Therefore, I live in Texas. Right. Now, this is a little bit more trickier. Right, so, and get a feeling that this is more like this one here. So, person live in Dallas and Dallas in Texas. Then I live in Texas. So this is more like the P to Q and Q to R imply P to R. However, this sentence have to be rewritten so that make more sense when we write like that. But the point here is it is this one kind of transitive properties. Right, next, if it is sunny, then I will go to the beach. It is sunny, then I will go to the beach. I did not go to the beach. Therefore, sorry, if it is sunny, I go to the beach. I did not go to the beach, not Q. Therefore, it has to be not sunny, not P. Of course, this is kind of like the contrapositive. So this is Morris tolerance for using the contrapositive properties. Once again, if the second one here needs this one need to be rewritten so that it makes more sense to use that. Right. Next, a valid argument is a sequence of statements. Each statement is either a premise or follow from the previous statement by rule of inference. The last statement is called the conclusion. A valid argument takes the form, so we have a bunch of statement, and if we have each statement is either a premises or follow from the previous statement, so that may be another premise or implies from the previous statement. Right, so we see how that works. Right, from a single P and P implies Q, why the conclusion here is Q. Right, so later on we write proof, but now we just write in the simple form of logic. So let's say if this is true, I'll just spell that. And this is a conjunction. conjunction is true when both of them are true. So we have P imply Q, and we have P already. Therefore, we have Q. Okay, so that is the first one. Yeah. So even though this is not one of the premises, but this premise is derived from that statement. Right. So we can certainly prove like that. Rules of inference for quantified statement. So this will be easy. Of course, all the name, forget about that. If you can understand the logic, it should be fine. Right, now, for every x, p of x, p of c works. Right, so if it works for everybody, it certainly works for c in particular. If it is true for every x, it is true for when x equal to c. That's simple enough, right? Now, p of c for an arbitrary, so the key here is arbitrary. So, and then the conclusion is we're true for every x. Of course, we can choose c to be anything. If it works for anything, then it works for every value of x. So this is kind of renaming things. Doesn't matter what we put in here. If it's true, doesn't matter what we put in there. It's true for everything. Of course, that's obvious. Right, next. If there exists p of x, then p of c is true for some values of c. That's what the exist means. The exist means some value will work, and that values we call c. And if it works for some values of c, then the p of x, there exists values that work. So that's just the renaming things, if you will. Right, and look at this example. Michelle got an A in the class, therefore someone got an A in the class. That makes sense, because Michelle is one of the members of the class. So that's why we say P, the statement for Michelle so if this one true, where P is getting an A, so if you substitute Michelle in, it is true. Therefore, I'll just say implies that there exists a person that get an A in class, and that person could be Michelle, could be certainly would be Michelle, maybe somebody else, but at least one of them is Michelle. So that's good. Next, everybody pass that R class. So everybody will pass the class, and you take the class. So I should say it. So of course, instead of write that, let's just instead of write that, let's just write in form of an argument would be better. Therefore, exists a person that get an A. Right. For every x, the P of x, that means there exists that means you will pass the class. Right. If it works for everybody, and you is one of those everybody, then it certainly work for you too. So that's what the argument is. We have a lot more of this in the next section, but now let's see how this works. for positive integers n. If n is greater than 4, then n squared is less than 2 to the n power. It's true. Assuming that this is true, so that 100 is that. So for every integers n that is greater than 4, and implies n squared is greater than 2 to the n. I'm sorry, less than, right? And then we have for 100. If you substitute 100 in, that certainly work. Right. Now let's rewrite this as the problem with the Socrates in the beginning. Let's rewrite this again. For every n, this n greater than 4, so we just replace this. If this is the case, then this statement, let's call that S, and it's true. Right, so we rewrite like that. Now we have 100. And this is true, of course, if you define g of n is when n greater than 4. If it's true, of course, when we substitute 100 in n, that will be true. And the conclusion is that it will true for 100. Of course, we're not going to prove like that in the next section. We're not going to write. But if we want to write an argument, it will be like this. Yeah, so that is just like the example of the Socrates being model. Right, like I said, it's just some briefly introduction of the tools that we can use in proving. But as you see in the next section and the section after that, we'll prove we might not need much of this. Most of the steps that we use is just based on the properties that we get from math. But for this section, I'm going to stop here. As always, thank you for watching.